So I'm introducing Orly Edlin. She will be giving a talk on controlling accelerators with machine learning. And I'm going to tell you about her background, and when you hear about it, you would think that right when she was applying for her undergraduate, she was planning this talk, because she charted a course that, so she did her undergraduate degree in physics from Rensselaer Polytechnic Institute with minors in several disciplines: philosophy, science, mathematics, psychology, and science, technology, and society. After graduating, she became a research engineer in the Theory, Modeling, and Analysis branch of the Naval Surface Warfare Center in Bethesda, Maryland, where she worked on the complex problem of reducing the electromagnetic signatures of submarines. How cool is that? In 2012, she brought her interest in complex systems optimization and machine learning to Colorado State University, where she became interested in applying her skills to particle accelerators. For her PhD, she used neural networks to model and control the accelerator system at the Fermi National Accelerator Lab. After completing her thesis, Orly joined SLAC as a research associate in the Accelerator Research Division, where she continues to work with a growing group of co-workers and collaborators on applying machine learning to practical accelerators. So without further ado, it's yours. Oh, you don't need this. Go ahead.
Thanks. Thanks, everyone, for being here tonight. This is a really fun opportunity to kind of share some of the joy that I find in working in this area with all of you guys. So I am going to start. Oh, is the sound not on? Oh, okay. I'm going to start by telling you a little bit about my background in the hopes that as I'm doing this, I can also talk about some of the concepts that initially got me interested in this area to sort of spark some of the frame of mind and imagination that comes around with a lot of this. So I grew up in the middle of nowhere in upstate New York, which means that I spent a lot of time running around outside, wondering about the world around me. And I think this is a big reason why I got interested in science. It was just fun to wonder about how all these different things worked. When I was in high school, I was already sort of interested in astronomy and physics, and there was a science essay contest that came up. And as part of this, there was a cash prize. And I wanted to write the essay, but I also wanted that cash prize so that I could go out and buy a telescope. So that's what I did. I won the contest. I got this telescope. And then I used it in my family's field, oftentimes in the cold winter months when the viewing is really clear. And I remember distinctly this first time that I was wandering out into the field. The snow was glistening all around me. I had this telescope with me, and I could look up at all these stars and globular clusters and nebulae. And I remember thinking to myself how cool that was, that I'm here on this tiny planet that has a socioeconomic system where I could write some words, some well-thought-out words, win a contest, use the reward from that to buy a telescope that now enables me to look at things that are thousands of light years away. And on top of that, using a tool that took hundreds of years of collective engineering to build. So that kind of way of thinking, I guess, is sort of the common thread in all of this. And when I went to college, I started getting really interested not just in physics, but specifically in complex systems. So these are things like the superstructure of the universe, where you have all of these interactions between different centers of mass, and it evolves over time in these sorts of really interesting ways. I was interested in the brain. How is it that we have all of these neurons that communicate, and somehow we take all of these collective effects from these small interactions and wind up interacting in the world in a reasonable way? Things like slime molds, which can actually solve complex optimization problems. Pretty bizarre. And even just things like social networks. What are these different clusters of connections that this person has? And the common theme in a lot of these systems is that they're really difficult to predict what's going to happen, right? So when we're trying to model the Earth and how things evolve on the Earth in terms of weather or like long-term trends like CO2 content, this gets really hard to predict. I mean, to the point where you need to run thousands of hours on a supercomputer to be able to do so. So this was all really cool. And I think at some point when I was working in DC, sort of evolved from this idea of just trying to understand and predict these sorts of things to what happens when you actually need to take a really complicated system and control it. So something like a tokamak, where you're trying to confine a really hot plasma and get some energy out of it. That's like a really hard, really interesting problem. And to kind of sort of highlight how complicated this can become, let's take a step back to the more mundane things. You all have the experience probably of stepping into a hotel bathroom, and you want to take a shower, and you have no idea really how to adjust the knobs on the shower so that you're not scalding yourself or freezing yourself. And at first, you're just kind of making small changes, seeing how things improve. But you're actually doing something more interesting than that, too. As you're doing this, you're also learning some model of how this particular shower system works. And in your own home, you probably know exactly where you need to set the knobs to get just the right temperature for you. So that's a really simple control example. And I thought that was kind of fascinating to think about this intersection between trying to optimize a system or control it, and also building up these learned models of it while you're doing that to improve control. And at some point, I became aware of accelerators and what a great kind of playground these are for looking at this kind of problem. So not only are they huge, you also have many parameters that you need to adjust, hundreds to thousands in some cases. And it's becoming more challenging to control these systems as we start going to more advanced kinds of accelerating technologies. Right now, a lot of people are trying to accelerate beams in plasma. So it's a pretty amazing thing, really nonlinear. There are also a lot of really great practical uses of these machines, reasons why you would want to have fine control. Right? So for instance, we want to be able to use accelerators to help treat cancer, and that requires fine control over the beam. So this is really just a very rich area to study this kind of task. In the case of the LCLS, we're dealing with beams, electron beams that are moving very, very quickly, close to the speed of light. Just to give some context, the energy gain of every single electron in the beam is the equivalent of using 33 billion AA batteries to accelerate that beam. And the beam can be extremely intense. So this is kind of a cool thing. It's a really unique instrument. And we can use it to do things like study photosynthesis. How does this work? How might that help us understand these systems better, but also maybe build systems that take advantage of that? How can we understand protein folding? And maybe that can help with drug design. Maybe we can also look at chemical reactions and how they're occurring and use this to develop new approaches to making different kinds of chemical reactions occur. And then we also can study things like really intense conditions, like what you might see on an accretion disk in a black hole, for instance. So this is the kind of science that this facility supports. And it's really heavily used. In 2016, there were just over 1,000 user experiments. And since the facility was built in 2009, there have been just over 1,000 papers published. And people wanting to run experiments that help elucidate these sorts of things come very frequently. They come for a few days to a week. And they have specific electron and photon beam properties that they need in order to do this science. So how do you actually support that? In fact, what we have is an accelerator that's very flexible. So we have a laser that comes in, it produces an electron beam. We accelerate it through different accelerating cavities. We have to compress the beam, which we do with a series of magnets, focus the beam, and then eventually, once it's sort of gotten to the right shape at the entrance of the undulator, we wiggle it back and forth to produce light, which is then sent to, at this point in time, 7 experimental stations. And in order to meet the needs of these different users, we actually have to span kind of a wide variety of beam shapes. So here I'm just showing different kinds of electron beam shapes that we might deliver to different users. In terms of how time-consuming this is, over the past few years, around 400 hours have been spent tuning per year, and intensive tuning is done on average 2 to 5 times per day, and on average this takes about 30 minutes to do for a new user. To put some numbers on this, the approximate annual budget of LCLS is about $145 million, and on average we've had about 5,000 hours of experiment delivery per year, and so this means that it costs about $30,000 per hour per experiment. So what this means is that tuning up the machine efficiently to meet these kinds of challenging beam conditions is really important. So in a perfect world, how would we do this? Well, if we had some accelerator model and we could just send a bunch of different adjustments to these various things that we can tune, we would get a perfect prediction and we could just apply it to the real machine. In reality, that's obviously not the case. We have lots of fluctuations that we can't control. For instance, the initial laser spot can fluctuate a lot. We can have pretty dramatic slow drift over time. We're actually operating a machine that relies fundamentally on an instability. And then on top of this, even if we wanted to run an optimization on our simulation of the machine, in reality, this is infeasible generally because we have really computationally intensive simulations that are needed to actually replicate the machine behavior well. In addition to that, we also often don't do that well matching our simulations to measured data. So there can be a big gap here. So in practice, what do? We rely a lot on human operators to tune the machine. And so they're doing all sorts of complicated tasks. These are really highly skilled people who have a lot of experience both with accelerator physics and with the individual machine that they work on. And for instance, they'll be doing things like looking at time series data that's constantly streaming on the fly. They'll be building up these internal mental models, both of how the machine behavior looks and also, getting a feel for if I change this knob, what can I expect to see occur given some overall collective machine state that we're in. They're also oftentimes doing kind of complicated image analysis, right? Looking at images of the beam. So there's a lot here that operators are doing, and oftentimes they'll also be sort of constantly tweaking the machine. So this is kind of analogous to this shower example that I talked about earlier. When you have that amount of information coming at you all the time, and you have a machine that's as complicated as the LCLS, it's really easy to miss kind of simple stuff. So this is an example from a few years ago where the FEL pulse energy suddenly dropped, and it was really difficult to chase down why that happened. It could be any number of things. One thing that doesn't happen so often is the cathode QE suddenly changing. In this case, that's what happened, and so sort of the last thing that anyone was thinking of. And it took hours to find out that that was actually the cause. If there was sort of just a simple algorithm looking at this, seeing that suddenly there was a change in the average cathode QE, this would have been caught immediately. And we could have had a flag out to the operators to say, look here, this might be where the problem is. So a big point of a lot of this work is really to see if machine learning can help out with some of these tasks individually, and also provide better tools to the operators as part of that. And it's also this question of, can we reach better operating conditions or find new capabilities if we can actually tweak knobs across the whole machine, if we can spend more time tuning the machine versus chasing down problems like this. So that's really part of the big vision. So I want to introduce, I guess, some challenges that come up in optimization in the context of having met all of these knobs that you're adjusting to try to come up with some specific beam characteristics. So we'll go to this kind of toy example where I might be a hiker that has decided I want to camp out for a while. And my goal is to camp out at the highest peak. But it might be really foggy out. Maybe I don't really know anything about the landscape that I'm wandering into. So all I can do is see if I take a step in some direction, am I improving or not? And so I can keep doing that, and eventually I come to some peak here. And then as I continue to move forward, I start to see that I'm starting to go downhill. So maybe I just, because I can't see what's going on, I just go back to this peak. But in reality, I'm only at this local maximum, and I've missed the peak that I actually want to be at. On top of this, if I stay here for a while, if it's snowing or something, maybe I'm camping out for months, and I want to keep being at that peak, this might drift over time. And so in order to actually stay on this peak, I probably have to keep optimizing continuously. So this is sort of a simple problem to think about in one dimension. But when you start talking about 2 dimensions, already this starts to look a little bit mind-boggling. And then when you're talking about potentially dozens to hundreds of parameters that you might want to optimize simultaneously, this starts to look very, very hard, and it is. So to look at an example of how this is done in practice on a real machine, we have, for instance, some Linac phases and some beam energy settings that we can control. And we can do exactly the sort of procedure that I just described, where you look at local changes and then slowly move these control parameters simultaneously in a direction that seems to give some improvement, in this case in the Xray beam energy. So here you can see we're slowly moving towards some better value for the Xray pulse energy. And in fact, if I have some major change that occurs, I can kind of track this. So I can account for drift in the system or sudden changes. But this changes a little bit if I have a model of the world around me, right? So this could be a GPS or a map in this case. And now, even if I can't really see what's going on, when I get to this point, I still know that I haven't reached the peak. And I know that it's out here somewhere. And so I'll keep going until I can actually verify, okay, this is where I want to be. This is where the peak is. And in fact, I don't actually have to walk there anymore. Maybe I can just helicopter in and land there. Convenient. Even if my GPS isn't perfect or my map isn't perfect, as long as things aren't drifting too much, I'm still probably pretty close to where I want to be. And I can just, walk around a little bit and get back up to the top of that now snow-covered peak. We've been trying to do the same thing with the LCLS. So for instance, if I have a target beam shape that I want in this energy position space, I can take a bunch of historical data and train a model to actually map some requested image that corresponds to this beam to some suggested initial settings that I might use to get there. And we did a test of this just with 2 parameters, because we weren't sure how well this would work and wanted to keep it simple. And then we also added in closing the gap a little bit with a local optimizer afterward, and compared this with just using a local optimizer. So we messed up the beam, gave it this target, and then what we found was that the local optimizer did indeed get stuck in a region of parameter space that it couldn't get out of to reach this target value. But when we had started with some initial settings from the model, we were able to get there. If the real system changes a lot over time, like we know the LCLS does, one might think that there could probably be a better way to incorporate this uncertainty in choosing control parameters. So, for example, if we know over time that we have this kind of variation in something like snowfall, maybe one year the snowfall was really crazy, but that doesn't normally happen, we can take all of this variation into account and form some model based on that has some error bounds. So we can say it's probably most likely going to be a maximum around here in any given year. And we can then go and go right to that point in our real world. Where this really starts to become useful is if you have a region that's totally unexplored. So maybe I've totally mapped out this space, but I haven't looked here very much. I no longer just have this picture. Instead, I have this whole other region that I haven't looked at all that has a really high uncertainty. And I might have some average that my model predicts, but it's likely to be wrong. The uncertainty is really high. And if I am just basing this on where my average is and where the potential, sort of how uncertain I am about how high this peak could be, this actually looks like it could be an even better spot than this spot that I know is there. So if I helicopter over and I look there, and I see that it's now, in fact, a better place to be, I now can close the uncertainty in my model about that point. And I still may not have a great idea about what's going on in these other regions, but I know a little bit better. And so essentially, exactly this sort of analogy is something that we've used at LCLS to tune quadrupoles. So in this case, quadrupoles are just focusing magnets that are used to make the beam size such that it'll go through the undulator properly. And we found over many repeated trials that if we use just sort of a standard local optimizer in this tuning process, we don't do as well as when we use this kind of machine learning model that has some understanding of both what's going on in the space and what the uncertainty is likely to be. But we can actually do a little bit better than this. We can include some physics. So we know, for instance, that 2 adjacent magnets will be kind of anti-correlated in the X-ray pulse energy. So we can actually encode this in the way that we set up this particular kind of machine learning model. When we do this, if this was our true system that we were trying to model, and we encode some expected correlation in the model, and we choose some points to fit, we actually wind up with something that represents the real system much more closely when we've baked in that physics understanding ahead of time. And when we test this on LCLS, we find that it does help quite a bit to have this physics knowledge sort of included ahead of time in the way that we've designed this machine learning model. And to again put some numbers on this, you can sort of see visually that this is a clear improvement. However, when we take into account the operating cost of the machine and the overall budget, you can estimate that this is about $600 saved. And this kind of tune-up is done repeatedly. So you can imagine that if you could do this sort of thing for a bunch of different tuning tasks, we can save a lot of money in the operating budget, and also potentially do more science because we're tuning up more quickly. You can also include things like requiring that the pulse energy doesn't go below a certain threshold, or that we're not losing beam into the beam pipe and potentially damaging the machine. And this works kind of nicely, and it's done in the same fashion as predicting the uncertainty of the output value that we care about. So you also predict how likely it is that you are to violate one of these constraints, and you avoid exploring those regions. So this has been tested at the Swiss free electron laser, and we're working to apply it to LCLS as well. Without including these safety constraints, you get a lot of intermediate dropouts in the X-ray pulse energy, which is not great for a user. But if you include these safety constraints, you don't have nearly as much of that behavior. And you're not dipping down to where this threshold is set at all. So far, I've only talked about one parameter, output. And in reality, in accelerators, we care about more than just one parameter. There are many parameters of the beam that we want to have conform to specific characteristics. So an analogy to this is if I just care about expense when I'm buying a car, it's sort of an easy trade-off to assess. I just have some threshold that I'm not going to go above. But in reality, I have other constraints. I might care about how slow my car is. Maybe I have some maximum level of slowness I'm willing to tolerate, for instance. So it's really a trade-off now between how expensive of a car can I tolerate and how slow of a car can I tolerate. And there are some good trade-offs in the middle. In fact, you can maybe draw some curve here and define some set of possible cars. Because if you have a car that sits in this corner, this means you've got a really, really inexpensive, really fast car, which doesn't exist. If you're up in this corner, unfortunately, it means that you overpaid for a really slow car. Or maybe you were just paying for some other trade-off. Maybe you cared more about energy efficiency and the environment. But in this space, we're just looking at speed and expense. So what this line really means is that this is the best possible trade-off between speed and expense that I can achieve. So for this dollar amount, this is the fastest car that I can get at that price point. But I could be anywhere in here. If I don't do my research, maybe I'll wind up paying a lot more for a slower car. So we want to do this in general for accelerators when we're doing experimental setup, experimental design. And the problem is that this really requires many evaluations. So on the machine, you don't really want to do that. And in simulation, it's too expensive to do that thoroughly. So oftentimes, we'll pick one or two beam parameters that we really care about. We'll look at a really narrow range of all these settings. We won't really explore the space fully. So a natural question is, can we improve this? And one way to do this is just to build essentially a model of the simulation. And you can do this using machine learning. And what you end up with is 1 million times faster execution than the original system. We've done this for LCLS. We've varied parameters over a really wide range that are used in operations. And then we find that the agreement between the simulation and our model is very good. So what this really means is that instead of, if I want to run one simulation of this with all of the nonlinear effects included, instead of needing a supercomputer, I can now run this on a laptop. And it also means I can now run it in the control room, which is pretty exciting. So next, the question becomes, well, can I actually trust these models when I go to run an optimizer around them? This is pushing it maybe outside of the exact region in which it was trained. This is an important question, especially for the use cases that we care about. So we've done some studies here at SLAC to try to start addressing this question. So essentially what we've done is trained some machine learning models and run the kind of optimization that we would normally run on a physics simulation on the machine learning model, and also run on the physics simulation. And then we compare these trade-offs, see if we get the same answer. So we've done this for kind of hard to simulate systems at the beginning of the accelerator. This is an injector. And we have a number of input variables that we're adjusting. And then we have a bunch of output beam parameters that we care about comparing against with one another. And what we find when we do this is actually that the answer that we get is very good. The orange line here is the optimization that was done with the ML model. And this, again, is just one projection. This is just two of the beam parameters that we compared. And when we run the solutions along this line for the inputs into the simulation, these are the x's, we find that it agrees really well. So this was kind of surprising and quite exciting. The really sort of amazing thing, though, is that to get the same exact answer, we needed 130 times fewer simulations. So really, what this means is that just to get this solution, not just to make sort of a faster packaging of it, we're talking about 19 minutes total, including making the initial training data, versus 36 hours. And then in the end, we've got a model that we can reuse as well. Another interesting thing is that when we compare the training data, which are all these orange dots, to the final solution, we actually have interpolated well in this really high-dimensional space and come up with a solution that doesn't quite touch the training data. So it's really sort of indicative that this is doing something more than simply just memorizing the training set. It's able to interpolate in this high-dimensional space. How far we can push this in terms of how high-dimensional we can go is an open question. This is an interesting initial result. Another major problem that we have, as I said before, is that oftentimes our simulations don't match our measured data. So if we train a neural net or some other machine learning model on simulation data, we'll still wind up with a model that's wildly inaccurate relative to the real machine. So now the question becomes, since we really can't afford to fully explore the parameter space on the machine, and oftentimes what you'll see in archived machine data is lots of fine-tuning around kind of discrete and separated operating points. So that's also not so great for trying to train a model. It's also really hard to work with real data on a huge drifting system. In simulation, it's a little bit easier. So we can do things like do really broad parameter scans. So now this question is, can we train a machine learning model in simulation data and then somehow update it with measured data so that we are actually producing some more accurate representation of the system that also will be applicable to regions that kind of lie outside of the training data set that we have from the measured data. And we've tried this with small systems, again, where we have a number of beam inputs, machine inputs, and a number of beam parameter outputs, and then done some fine-tuning based on measurements, and we're able to close that gap quite a bit. And the really important thing here is that you don't get this kind of accuracy just training on the measured data alone in this case, because we had so few measured data samples to do it with. So this is another interesting area that we're exploring and trying to apply to larger systems like the LCLS. Another kind of important area that a lot of us are interested in is whether or not we can actually learn something from these machine learning models. Can we find kind of unexpected correlations in the machine that nobody knew were there? And it seems like we can to some degree. So at Spear 3, which is here at SLAC, if you look in the data archive, the efficiency with which they're injecting into the ring varies quite a bit. And the operators were constantly kind of adjusting feedback settings in order to chase this and make sure that it didn't drift too far below what they required. So what they did was take a machine learning model and threw all of this archive data at it, and found that it was able to predict reasonably well. They used a bunch of measured inputs from the machine. And when they look at the sensitivities of the output to these various input parameters, they found that there was a really strong correlation with a ground temperature sensor in the parking lot. And that's not likely something that someone would have found on their own, just digging through the data. So now, other than being kind of funny, the useful thing here is that now they can most likely just look at this ground temperature sensor and then, based on that, get some idea of what the ideal position set points are, and just punch those into the machine, and then hopefully they don't have to do as much reoptimization. So another area where there's a lot of interest and a lot of work being done is trying to use machine learning to extract more information out of a lot of these complicated signals that we get off of the machine. So for instance, we have lots of images of the beam. We have things like RF time series readouts. And just to give you a couple of examples of this, we have at the LCLS this really nice diagnostic that gives us this energy time image of the electron beam. And this is used frequently in user operations. So for instance, you can take an image where you've suppressed the lasing process. So you're steering the beam in here in a way that doesn't allow it to actually produce a photon beam. And then during the experimental run, you can constantly be taking these images. And these spikes here that you see are actually indicative of the electron beam giving up some of its energy to the photon beam. So what this does is it allows you to use the combination of these two images to infer information about the photon beam that you normally wouldn't have access to. So this is called the Xray power profile. The problem is that this is kind of a slow algorithm. It also fails in cases where these spikes start to kind of fold over on one another because it's just looking at vertical slices of the image. So this question now is, can we use a neural network to look at this image directly and have better information about like how different positions are correlated with one another, and then get an estimate of this Xray power profile more quickly and maybe a bit more accurately? And we've started working on this, and there's some initial results that look pretty promising. So this blue curve is the traditional reconstruction algorithm. And then the red curve is the prediction that we get from this convolutional neural network that we've trained on lots of simulation data. And the green, which you can barely see, is the actual predicted Xray power profile. So this is already outperforming the standard reconstruction algorithm. How this will translate into the real world, how well this will generalize to new machine states, these are the kinds of much more challenging open questions that we're working on trying to answer now. Another major area of interest in the community is, can we use these kinds of techniques to identify when something is going wrong with the accelerator? So for example, for LCLS2, which is an upgrade to LCLS, we're relying on superconducting radio frequency accelerating cavities. And these are really sensitive. They also have these very large cooling systems associated with them, which have their own complex behavior. And if one of these cavities fails in what we call a quench, it can be pretty bad. This cryoplant can take a while to cool back down. We can damage the cavities. It also affects user time, obviously. And it's not so simple. It's not as though these things fail the same way each time. So right now, oftentimes, experts sitting in the control room will look at RF waveform data and try to figure out what kind of quench does this look like, what kind of actions can we take, or if they're looking at a past example, did we take, how effective was that, how can we fold that into improving next time. And this is, as a result, kind of a slow, laborious process. At Jefferson Lab, they've started doing some work that instead uses various machine learning algorithms to look at these signals directly and automatically classify what kind of trip it is. And then now that they've implemented this system, they're building up this huge database of examples of types of trips, what action was taken to try to recover from that trip. And hopefully that'll help them figure out new ways of informing, if suddenly from the control room I get a signal that this type of trip is happening or is about to happen, maybe now I know better what things I need to change, like lowering the amount of RF power going into the cavity by a certain amount, in order to either avoid the really bad consequences that might come out of that trip or just recover from it more quickly. Sort of a similar example where you're trying to figure out whether to trust a signal or not, or whether something's going wrong with that signal, is this case of trying to assess when a beam position monitor might be giving you a faulty reading. So in any accelerator, we have some ideal beam trajectory or beam orbit, and oftentimes what you want is this just to go along the center. And the way that you do this is by adjusting steering magnets along the beam line. And along the whole thing, you also have beam position monitors that can tell you how offset you are in the space. But sometimes these give you bad readings. So if you get a bad reading, you really don't want to be adjusting this magnet in order to compensate. Maybe this reading says that the beam is way over here, so then you make this magnet really correct that beam to go way over here. But if this reading was wrong and the beam was actually in the middle, now you've steered the beam into the wall. This is the sort of thing that you want to avoid. We also use beam position monitors to get some idea of what the kind of optics overall in the accelerator are. So you also don't want to be subject to these kinds of errors when you're trying to get a measurement of what's going on in the machine. So we have standard techniques to deal with this, but it's not totally perfect. It won't remove all of the bad BPM signals. A group at the Large Hadron Collider has been using machine learning to try to classify when a BPM is giving a bad reading or not, and then throw it away before using it in a correction or using it to give some information about what the machine's doing. So this is just showing how many spikes, how many bad BPMs are removed with the standard algorithm. This is the number that are still remaining afterward. And then these last few that are really tricky to identify, they were able to remove with a clustering algorithm called an isolation forest. And they also found that when they apply this to their optics measurement, they wind up with a much less noisy signal. So this is a much more reliable estimate of what's really going on in the machine. So overall, each of these applications kind of fall into a few major use cases. So we want to use machine learning to help speed up system optimization. We want to have faster models that are more accurate relative to what's really going on in the machine. We want to be able to get more useful information out of all of the machine signals that we do have. We also want to find out if there are hidden sensitivities in the machine that we could maybe take advantage of to help out when we're trying to do tuning. And then we want to detect when something's going wrong in the machine. We'd also like to predict when something bad's about to happen. Like if we can predict an RF cavity quench, maybe we can avoid it altogether. So I showed a lot of work from what's sort of a growing international community that's interested in this particular research area. So in February of last year, we had the first machine learning for particle accelerators workshop. This was kind of the first time people who were interested in this area came together and exchanged ideas, talked about challenges that they have at different facilities. It may look like a small group, but this is growing rapidly. And now at SLAC, we have a small group that's working specifically on applying machine learning for accelerators. So many of these people are actually kind of full-time working in this area, which is pretty exciting. And I think in general, a lot of the consensus in the community is that machine learning is really a complementary approach. It's not going to fix all of our problems. It's something that provides a set of useful tools that we can maybe use for some of these specific areas where we know we have a need. But overall, it's been sort of not such a well-explored area yet. There's a lot of opportunity to try new things and see what's going to work and what's not going to work and get big performance gains. And along with that, I mean, we're very much still in the R&D phase. Like we don't know fully what's going to work, what a lot of the pitfalls are going to be. We know that there are a lot of open questions about how to update our models over time, how to have some prediction of model uncertainty along with just having some raw beam parameter output, these sorts of things. But the general hope is that by using these tools and kind of figuring out what works and what doesn't, we might be able to open up a lot of new capabilities. So maybe we can reach more challenging beam configurations at the LCLS that we weren't able to do before by just tweaking lots of knobs simultaneously, or getting some better understanding about sensitivities in the machine that we weren't aware of. We also might actually be able to help out a lot with optimization of systems that have traditionally been really, really difficult just because they're so nonlinear and so complicated, really hard to tune. Things like plasma-based accelerators, for instance. In some cases, machine learning might not just be a help here, it might actually really make some big leaps forward as far as being able to do sort of larger scale system optimization to bring things like the energy spread down for these types of accelerators. We also, if we can speed up our simulations, maybe we can do more thorough optimization. Again, tweaking lots of knobs across the whole machine. Maybe we can plan out our experiments better ahead of time so that we can really set up the machine well right at the start rather than doing a lot of kind of hand tuning during the user run. We also have a lot of opportunity to improve existing capabilities. So simply doing faster tune-up and avoiding failures, that'll enable us to do more science. It's also definitely important that a lot of these tools are used to really help the operators do things a little bit better. So for instance, if an operator can see that a certain kind of trip was about to happen with an RF cavity, that helps them out a lot, because then maybe they don't have to spend the next 30 minutes trying to figure out what kind of trip that was. It also, this is also a case where we can take technology that we're developing for accelerator systems like the LCLS, and maybe then transfer it out into the medical and industrial setting so that we can do things like finer control over beams for proton therapy. So going sort of out of the R&D stage to tech transfer. It's also, I think, important to note that a lot of what we're working on likely will require a lot of development and support at the beginning. But so far, a lot of the initial signs that we have are that this should pay off. Everything looks fairly encouraging. It's also kind of an interesting way to tie in machine learning research. We actually have a pretty unique set of systems. We have a lot of data. We have a simulation of the environment that is somewhat good relative to the real system, unlike something like a self-driving cars model of the whole world that's very hard to simulate. We also have really high-dimensional parameter spaces, and then we have these issues where things are drifting over time. These are kind of really interesting, challenging systems to work with from the machine learning perspective. So there's an opportunity to give back to machine learning research here as well. So with that, I hope that this gave you kind of a high-level view of the things that we are looking at and wanting to do with machine learning for particle accelerators, and that this is kind of an opportunity to think about, what else could we do? What new things could we do if we start using a lot of these tools? Thank you.
So if you have any questions for Orly, please press the speaking man button on your microphone. Yes, please.
I'm a little confused. You've got data from operating the system, and you've also got a simulator. Which do you use to train the neural network?
Yeah, so ideally we want to use both, right? But on their own, individually, they both have their merits, right? If I simply want to take a really slow simulation and I just want to speed it up, I don't actually need to use any measured data. I can just generate my simulation data, train my model, and now I can just use that as a faster executing version of what I had before. If I am working with a system where I don't really care about using it for optimization, right? Maybe I just want a prediction, and I know I'm not going to be going into new machine states. Maybe I just want to do really well at predicting some information based on some other measured data. In that case, you may not really care whether you're covering other regions of the parameter space as well. So then maybe you can just take a chunk of measured data and just train on that.
So the simulator lets you go places that you haven't actually operated in.
That's correct.
I see, thank you.
Yeah. It also helps as far as actually being efficient about how you're training the model. So for instance, if I only have enough beam time to get 300 data points on a given machine, that's not enough to train something like a neural network model. But if I have a simulation of that part of the accelerator, I can just generate a ton of data with that, train my neural net, and then fine-tune it with the 300 data points that I have. And then I'll wind up with something where the simulation is giving me something close enough to the right answer that it only needs those 300 data points to converge. So there are all sorts of ways where you can usefully combine both simulation data and measured data.
Has the the default operator tools actually been changed in accordance with the machine learning results that you've gotten?
Yeah, so for the Gaussian process work that I talked about, where we were trying to maximize the FEL pulse energy by adjusting focusing magnets, that's been fully integrated into the LCLS operating system and actually has reduced tuning time for that task quite a bit over the past year.
Great.
Really fascinating work. I just have one question I want to ask right now. What packages or libraries are you using primarily in your research and development?
Yeah, so speaking for myself, I tend to use PyTorch. I also, for simple prototyping, use Keras. For doing optimization, there's a package called DEEP, which is really good for multi-objective optimization and evolutionary algorithms. A lot of other people in this area who I work with find that Keras is often all they need for a lot of these problems. Much of what we're tackling right now is still simple enough that we don't need the performance enhancement that you get from using PyTorch or raw TensorFlow.
Maybe a bit more of a generic question. I thought it was really fascinating to see what a step up you can get in performance from using neural networks rather than the previous simulation you had. Do you think we're reaching a point in time where maybe improvements in software are overtaking Moore's law in hardware? And if so, would you expect to see sort of a Moore's law equivalent in software going forward?
Yeah, that's a really interesting question, and it's one that I'm frankly not really qualified to answer. What I will say is that there's a lot of work that gets put into making particle accelerator simulations themselves faster. That includes things like converting the code so that it can run on GPUs, converting it so that you can run massively parallel simulations in an efficient way, because you're dealing with essentially a cloud of electrons, and they're all interacting with one another. So this is something that you can parallelize that computation. I guess the real takeaway for me from that particular line of work, where we've used some simulation data to train a neural net, is that this is now something that once took many minutes or many hours to run, that I can now package in a way that can run on my laptop in under a millisecond. And to most people that I've talked to, that seems like something that we would have a hard time getting to just purely algorithmically on the simulation side. Certainly, if you have some extremely large supercomputer and you have tens of thousands of core hours available to you on it, that's one route to speeding things up. But in terms of commenting on scaling laws and sort of what fundamental limits we might be hitting with regard to computation, I can't really comment.
Thank you for a wonderful talk. Could you say more about the parking lot temperature? There must be a good story that follows that.
Yeah, so actually, a lot of the speculation around what that might be centers around the fact that you don't have perfect temperature control of the actual accelerator itself, right? And these are all components that'll expand and contract thermally. So it's possible that the parking lot temperature sensor it's underground, is really just giving you some indication of how much thermal expansion or contraction is really going on in the actual accelerator. And this kind of makes sense. Nobody's gone and verified whether that's the case, measured distances or things in surveys between some of the summer months and some of the winter months, but that's sort of the reasonable explanation that comes to mind. I'm sure someone will dig into it further.
Okay, well, let's thank Orly again for an excellent